lecture in the morning, and I believe tomorrow morning's lecture, as long as you're up for it, Renato, but we'll check in, okay? So that is at least the plan, but you and I can communicate afterwards, but he's certainly giving this morning's lecture. And then we have an afternoon lecture today by Benabento, and then our first hands-on session this afternoon. And again, I realize that, given that this is online, tomorrow morning's online, just for those of you who are joining us online, keep in mind that it'll just be easier to do some of the work for the hands-on lectures if you are in person. It's going to be a lot easier, and we're going to have the help from Denise as well. Renato, I believe you can share your screen, so please feel free to do that now. And the only other thing to note is that you must use this microphone if you want to ask a question, okay? So rather than me sort of running around, I'm going to leave it off, but put it one on one side, both microphones, is that true? I'm going to leave them on the sides, and so just sort of pass them around. Okay, otherwise I have to just run around like crazy. It doesn't make sense. Renato, it's all yours.
Thank you, Joshua. So, good morning, everyone. It's really a pity that I can't be there with you today. It's a proof that, well, if we need to remember that COVID is not over, right? So here we are. Well, to start off, right, so let me present myself. I'm Renato Coutinho. I'm a professor at the Federal University of ABC. For those that don't know, this is the metropolitan region of São Paulo. So it's pretty close from where we are, right? And I worked a lot on COVID modeling. I already worked with epidemiological modeling before, but when COVID hit, it was like all hands on deck, right? So so a lot of work on COVID and on a lot of different topics and so on. And today, what I want to talk to you about is it's a case study on using models to analyze, to assess transmissibility in reinfection of variants, right? So we are going to. So this is one paper that we did that was really nice and really important at the time. That is the analysis of the P1 variant, as it was called then. Later, it was called the gamma variant, right? So, but today, like I want to go back a little in terms of giving some context and to understand the choices and to understand the processes, right? So this I want to give a lecture and not a research talk as such, right? So I don't want I want to take some lessons in general, right? Not only presenting this particular case, but of course this is interesting because it's an example of stuff that we have to face sometimes, right? So to start, to give a little bit of context, right? So Manaus is a large city, is 2 million people in the north of Brazil, and it was the case that at the end of 2020, right? We had this situation here, right? So we had already had a large epidemic in the beginning of the year, in April and May, like in this plot we have here. This is number of new hospitalized cases or hospitalizations in the city per week, right? So, and there was this study which was pretty polemic at the time, right? So that used serological testing and so on blood donors and so on to argue that 3/4 of the population had already been infected by COVID, okay? And then I'm not sure if the result itself was as polemic as the implication that it had at the time, because at the time in 2020, it wasn't so clear that reinfections were possible, right? So we had a few reports And I'm going to repeat, maybe I repeat some stuff that you have already known before, but I'm not sure if everyone remembers so well what was known at the time, right? So at the time, we had this idea that first off, right? So how do you document your infection, right? It's not so simple because at the time, the gold standard, and still today, right? The gold standard for detecting COVID was the PCR test, right? So you go, you have a PCR, positive PCR, then you have COVID and so on, right? And the funny thing is that some cases kept testing positive for more than a month, sometimes 2 months, right? So it wasn't clear. So, and it was the same case, right? So you see, it's possible for someone to have COVID and then the symptoms pass, but the PCR test keep coming positive, okay? And then it was defined in terms of documenting reinfection that in order to be sure that you have reinfection, you have to test PCR first, and then you have to wait at least, I don't know, 2 months, and then you have to PCR test again, and then you have to genomically compare these two different infections just to check that they are actually two different infections and not a kind of a resurgence in the body of the same infection, you know? So, and with this very strong standards for reinfection, what happened is that at the time we had very, very few, but at the time, I mean, at the end of 2020, we had very, very few documented cases of reinfections, right? And it was thought to be very rare, right? And what does this link? How does this link with what I said before? It means that if 3/4 of a population has already been infected, the potential for a new epidemic, for a new wave of infections, is much, much, much lower, right? So you have probably studied already, have seen SIR models, right? So SIR models, what do you have? Well, you start with an epidemic, and then a lot of people get recovered, and then you don't have enough susceptibles at the end of this epidemic. You don't have enough susceptibles to keep the infection going, right? So you end up with no infections at the end, no new infections at the end, right? So this paper here was very polemic because it got into this political battle about, well, should we keep taking preventions for against transmission if most people have already got it? Then, and the assumption behind it was that there wouldn't be a new epidemic if these people are not going to be infected again, right? So that was the situation, right? And then, of course, what happened later was that there was a new epidemic in Manaus, right? So even larger than the first, okay? At least the peak was higher, right? Not in total number of people, but the peak was higher, right? So it began in December, more or less, and then it went over January, right? January 2021, right? And it was quickly identified through genomic analysis that this was a new variant of concern that was called P1. I will use P1 here, okay? So, but this is also the gamma variant, okay? And you see here, I like this plot because it has some timeline here for, you know, when restrictions were eased, right? When you had an increase because at the end of the year we had entertainment venues reopen, we had also local elections that increased exposure and so on, right? And you see, we have to then look at this, right? And we have to go back in time to beginning of 2021 and think in terms of, well, when you look at this, right? We stop here, right? How can we assess what is going on, right? Because of course, we're saying, well, in Manaus, right, a city that was perhaps the one most affected by COVID in the whole country, right? It had a large epidemic, and so the potential for spread to the rest of the counties of ours is immense, and for other counties as well. And we want to do what, right? We want to be able to assess the impact of this, right? So how is this going to affect other places, right? And so, well, how do we do that, right? So if you have a new disease, right? So if you remember at the very beginning of COVID, okay, we had some estimates of transmissibility of COVID and how severe it could be, right? So what do I mean by that? How many people among the infected people are going to be hospitalized or are going to die from the disease, okay? So this is the main stuff that you need in order to assess a new disease. But with a disease that is already going on, right? It's already affected a lot of people. You also have to take into account immunity, right? So a lot of people have recovered already. So what do we need? We need also to estimate parameters or effects related to how much protection or lack of protection previous cases conferred, right? So you're going to build a model for that, right? So it's not just that we want to do this because it's interesting, but also because it's a very practical matter, because you need to be able to say, well, in this place where, for instance, you could do all kinds of hypotheses here, right? You would say, for instance, that the virus is very, very it is not so transmissible, but it can affect, reinfect anyone with equal probability or with equal easy, right, of infection. Or it would be the other way around. It would be that it doesn't reinfect so much, but it has a much, much higher rate of infection, right? So a much faster spreading. And depending on the answers to that, we need to take into account to assess the potential impact in other places, right? So it's really it's not really a purely academic research, right? So here, and this is perhaps the in our research talk, I would probably go very quickly through this, right? So I can say, well, we built a Sayer-like model with age structure, including severe cases and deaths, and 2 variants, and this is the original variant and the P1 variant. And what is the difference of the new variant with respect to the original one, right? So we assume that it's pretty much the same in terms of I don't know, incubation time, recovery times, and so on. And but then it can have different transmissibility and probability of reinfection for people recovered from the original variant. And it can also change this IHR. I'll use this term, right? IHR, that means infection hospitalization rate. That is, among infected people, what is the proportion of those that are going to end up in a hospital, right, with a severe case of COVID, right? So, and this is, this hides a lot of stuff in here, right? So there are a lot of choices here. And so I could go quickly through this, but actually I think it's interesting to go deeper into this, right? Because when you see them, if I go through this quickly and go to the results, it's possible for us to think that maybe this was a kind of obvious choice, or these are all this model structure, right? Those are all choices that we have to make, right? And so when you are modeling epidemics and so on, you always have a lot of choices, right? A ton of choices. And then you need something to guide you, right? So let's talk about some of these choices, right, first. So the first one is, well, I think Roberto or Joshua yesterday had thought a little bit about this kind of model structure, right? So you have SIR models that are susceptible infection infectious were over. And you have also SEIR models where you have this exposed compartment, right? What is that? It's an incubation period during which the person doesn't show symptoms yet or is not yet infectious, right? In the case of COVID, usually this incubation period, it is considered that that it's possible to infect. People don't have symptoms yet, but it's already possible to infect other people, right? So this not only makes a different timing from until symptoms, but it also contributes to transmission, right? But when you look at the pattern, right, if you look for at a SIR, right, if you plug it into your computer, right, and then you run simulations and so on, if you look at an SIR curve and an SEIR curve in terms of number of infections, recovery, and so on, they are very, very similar, right? So they show pretty much the same behavior in terms of, well, you have an epidemic, you have the exhaustion of susceptibles, you have a peak of infectious individuals, and then you have recovered increasing until it reaches a point where the epidemic stops, right? And infectious individuals go to zero. So qualitatively, they are very, very similar, right? To the point that you can, just by looking at it, you can not even distinguish the two of them. But quantitatively, right, if you want to fit these models to data, right, we know from experience that SEIR models tend to be much better, right? Why is that? Because when you look at an SIR model, right, you have only a single parameter for recovery, that is this minus gamma I, right? I think I have solved this before. And really the only parameter that you have free is the transmissibility rate, usually the beta parameter, right? So and it is interesting that even when you have an exposed compartment, even if you also fix, you have an incubation period and then you have the recovery period. Okay, you have an extra parameter that you also fix, right? So it's not that you're adding parameters to the model. It's also a parameter, a value that you know from clinical data, right? But even so, usually the SEIR model tends to describe better the data than SIR models, right? So this is a choice from experience, right? And the second big choice here in terms of model structure is which severity classes do we use, right? So we're going to say that after the incubation period, where you have this exposed class, we're going to divide people into people that are hospitalized. Why do we do that? Because we need the number of hospitalizations, because the data I just showed you before, right? So all this data here, they're not total number of cases, right? They're all hospitalizations, right? Because total number of cases is the kind of data that we never had throughout the pandemic, right? So there's no reliable source for that. Okay, so we need something that is more reliable, and that is hospitalizations, right? The other data that is pretty much really reliable is also number of deaths, right? The issue with number of deaths is that it takes much longer for us to consolidate the data, right? So if you have a peaking number of cases today, it can take like from 1 to 2 weeks for that to appear in number of hospitalizations. And then it can take another 2 to 3 weeks to appear for this peak to appear in number of deaths, right? So you see that in this curve down here, right? How the number of deaths trails the number of hospitalizations by a margin here, right? And this time can be critical, okay? So and then there's even the problem of and I won't go into detail here. I think other people, maybe Roberto at the end, I don't know, will touch this topic. This is ongoing, right? So if you are in January, I have this nice error here, but actually we didn't have all of this data in January, right? So because hospitals take some time to notify to include this data into public databases. And then what you see is actually something much smaller than this, right? I don't have the numbers here, but when you look at the number of hospitalizations in the last week, is always, even if you're in the middle of a peak, it's always much less than in the previous week. Why is that? It's because you have a delay notification. Sometimes a case arrives in the hospital and it takes several weeks for this case to be notified in the database, right? So you have statistical methods to correct for that, right? So this is what is called the nowcasting. But I won't go into details here, right? So we were at the time using already corrected data, right? So we got the raw data and nowcasted it to have an estimate of the real number of hospitalizations, right? But anyway, going back here, what we do have is hospitalization data, right? So in order to compare data to models, we have to have something in the model that corresponds to the data that we have, right? So we certainly need that, right? So the other choice we have here is that we also included asymptomatic infections. These were already known to be important at the time, right? So asymptomatic infections sometimes are thought to be to have a lower viral load, but on the other hand, asymptomatic individuals tend to take less care in terms of not avoiding contacts and so on. So this would make this would compensate for this lower viral load, right? And finally, number of deaths, right? So we are going to say that some of those severe cases, hospitalized cases, are going to lead to deaths, and this is also useful later if we want to compare this to observed number of deaths, right? So we actually didn't do this, but we might, right? So now, if you have questions, we have time. We will have time for questions at the end, right? But if you want to ask anything earlier, you can. You know, I don't see anything here, but someone is Josh. I think is controlling the mic over there, right? So you just ask them. Okay.
Yeah,
The second
we have,
topic in
Renato, we have multiple mics going, and also I'm monitoring
Oh,
the
okay.
chat. So if people are compelled for questions, but so far I think they're listening in.
Okay, thank you.
Okay, keep
So
hydrating.
this, sorry.
It was another
Okay,
hydration joke. Keep going. Keep going.
Okay, sure. So second one is age structure, right? So I told you here that we were structuring by age, right? So what does this mean, right? So we are going to subdivide the population by age. So we already know that, and it was very clear from the very beginning that COVID was much more dangerous for older individuals, right? So the risk of hospitalization and death was much higher the older you were, right? So for individuals at age of 50 to 60 was already much higher, and for 60 to 70 even much higher, and for 70 to 80 even higher. So there's a strong dependence on age, right? So when you think in terms of age structure, usually there are two possible reasons to include this in your model, right? The first one that is very usual is when you have childhood diseases, right? So usually these diseases that you usually get as a toddler or as a child beginning school and so on, right? And this is because you can renew your susceptible class through new people being born, right? So if you look, for instance, at historic cases of measles, there was a clear pattern of whenever you had a new cohort, a new string of children that didn't have measles before, eventually you have a new epidemic, right? Because the ones that were there before had already had measles, but they are no longer there. There's now a new cohort that is susceptible, right? So you have this renewal of the susceptibles through new arrivals, new births, right? So this is important when you are in an intermediate or a longer time scale, right? But for this here, we are trying to analyze what happened only during about 3 months, right? So we have here, we are here, right? So we are going to look only what happened from here, maybe middle November, beginning November, until end of January only, right? So this is at most 3 months, right? So we are not really changing much in terms of number of susceptibles, only in 3 months, right? So so really the second thing that we can lead us to include age structure is this: when disease outcomes are strongly dependent on age, as we have with COVID, right? So we have older people much more susceptible to hospitalization and death, right? So and this is important. Well, you could think in terms of, well, but this is only a proportion of the total number of cases, right? So if you say, well, if I don't consider age structure, right, I really don't want to do this, couldn't it be that hospitalizations are just going to be some constant proportion of total number of cases? Well, sure, you could you could say that, right? But then the issue you have with that kind of hypothesis, right, it's not so much that it's bad, it's just that it doesn't help you to generalize what happens in one place to what should happen in another place. So suppose that I have here, I go for this analysis without considering age structure, and then I have some parameters that are going to say, well, on average, you have this transmissibility, you have this rate of hospitalizations compared to total infections and so on, right? But if I now try to use the model that we fitted in Manaus and use it to apply it to estimate what could happen here in Sao Paulo, right? It doesn't work so well because here in Sao Paulo, we have a different proportion of young people to middle age or intermediate adults, right? So adults and older people than in Manaus, right? So you do try to avoid this, but then your model will lose in terms of generality, right? Because it's hard to correct for different age structures in different places, right? So when you include this directly into the model, the parameters themselves already take care of that for you, right? So this is a strong case for using this age structure, right? And the last one is that transmission is also strongly dependent on age, right? So we know this for many diseases, right? But especially for respiratory diseases, in normal situations, not during lockdowns, but in the current situation, for instance, children usually have a lot more contacts in their daily routines than do adults, right? Because they're usually in large classes, a lot of contact with other kids and so on until school is really a place that is really ripe for contagion, right? So usually children have a much higher rate of contacts between people of those ages than adults and older people, right? So I don't know if you have, I talked to Roberto, he told me that you haven't seen much in terms of age structure yet, right? So let me talk briefly of how do you do that, right? So I will share my other screen here, right? So let me go back here. Just a moment. Let me share this. Here it goes. Can you see my screen? Let me remove this stuff here. Yeah, okay. So yeah, I do like, I cannot resist, right? So I'm in the math department, right? So I cannot resist whiteboard, right? So yeah. How do you do age structure, right? How do you do age structure? Let's think about a SIR model, right? So if I have an SIR model, right? So you have seen this before, right? You write something like this: GT, GRGT, right? You have these boxes here. I could have done this better, right? Yeah, okay. I'm really out of practice after stopping the remote classes, right? So you have something like this, these boxes here, and you have something like this. Okay, I won't go into details here. I'm assuming that you are already somewhat familiar with this. Okay, so you have new infections in this term here, and then you have reovering here, right? So infectious individuals being reovered. Okay, but now let me say that for simplicity here, so that we don't spend too much time on indexes, right? So I assume that I have two ages, right? Two age classes, right? So for instance, two age classes, right? For instance, I have young people, young and old, okay? And I won't say at each age, at which age I'm going to divide young from old, right? So, okay. And all this 1 and 2, right? Age class 1 and 2, right? And then I have to say, okay, I have the whole population, and I have the total population, and is now divided into two, right? So population of young people and old people, okay? And then I have to write down now new equations that incorporate this, right? So it means that now I have essentially the same equations, but now I'll have S1 and S2 classes, I1 and I2 classes. So all of the equations will be doubled, right? We'll have an equation for S1, another equation for S2, an equation for I1, another equation for R2, R1, and R2, right? So this whole here will happen for each age class, uh, but not independently, right? Why not independently? We cannot really write this independently because old people do infect young people, and young people infect older people, right? So we have equations that will look like this. So this is pretty much the same. So this is GS1 dt and GS2 dt, and so on, right? And here is the thing, right? So we have that you have an infection rate that should be something like this, times I. So this is proportional to S1, and this is proportional to S2, okay? So far so good, but then by the population of, no, the population, yeah, of each class, no, total population, right? So yeah, this is, there are different formulations for this. I think this is more common. But now here, you have to take into account both infectious individuals, right? Both from the two classes, okay? Good. But now there's something else here, right? The thing is, in terms of the example I gave before of children, right? Children are much more, is much more, I mean, their contacts are much more often with other children than with adults or older people, right? So if you think of S1 as, and this is a general observation, right? So you tend to have much more contacts with people that are closer to your age than with people of very different ages, right? And then what does that mean in terms of epidemic modeling? It means that the way I wrote it here is not really very nice, because it means that individuals from age 2 and age 1 are going to have the same infection rate, the same chance of infecting young individuals, and it's not really true, right? So how do I change this, right? So the best way to do this is, instead of writing this, right, you are going to write something like this. You have S1 over N, a minus here, and you have individuals you have specific terms here, right? So I say that beta ij is contact rate of age 2 infecting, age J, right? Not age 2, age J infecting individuals from or of age I. Okay, so far so good. Raise your questions. Raise your answers. Raise your hands if you have questions, right? So, okay. So, and now there's and of course, when I write the GI1 dt, of course it will be the same, right? With a positive term here, right? So, and the same for the GS2 dt, right? So this is S2 over N, and now I have beta 21 I1 plus beta 22 I2, right? Well, okay, this is nice. This is nice, right? So you see that we have actually this beta, this contact rate, right? So I have contact rate of 1 with 1, 1 with 2, 2 with 1, and 2 with 2, right? So this, we can write this as a matrix, right? Beta 1, 1, beta 1, 2, beta 2, 1, beta 2, 2, right? And I can actually write all these equations in vector form, right? So this is very practical, right? So I can write down, I can write down the term that appears over there, right? So I can write beta 1, 1 I1 plus beta 1, 2 I2 as, I can write a vector I, and I can write this as beta times a vector I, right? So I is a vector that is maybe a column vector, right? I1, I2, right? So this is a much easier way to write this, right? And then we can just say, well, I can just write the full equations as a vector equation, right? And then this here things is a little bit more confusing, right? But this will be 1 over n. So this is S, the whole matrix beta times the whole matrix I, and then I have a product that is term by term term by term product, right? So I have to take yeah. Is that clear? Like if I do this product, right, I'll have two. So this here actually, if I multiply it, let me go back here. If I multiply this matrix with I1, I2, right? So the first, yeah, let me do this explicitly, right? So I don't confuse myself, right? So if I do this, so actually I have to take the first index of this, right? So if I do beta times I, this is beta 1, 1, beta 1, 2, beta 2, 1, beta 2, 2 times I1, I2, and this is going to be a vector that is beta 1, 1, I1, beta plus beta 1, 2, I2, and the other one will be beta 2, 1, I1 plus beta 2, 2, I2, right? So I have a vector that has two elements here, right? So the first one here will appear in the derivative of ds1 dt, and this one will appear in the derivative of that ds2 dt, right? And then if I multiply this term by s1 and s2, right, I'll have a vector with two elements, and this will be the derivatives that appear here, right? So this, when I do this, right, so this is this end of product here, where I take element by element, right? So the first one with the first one, the second one with the second one, to give you a new vector. Okay, so this is pretty much how you build these models, and I will show you a quick example, right? So let me stop sharing this here. So let me give you a very quick example of this, right? So here it is. Okay. So I have here a Jupyter notebook with this where I have some Python code to run this, right? So here I essentially did what I just told you, right? So GSIDT is a lambda, where lambda is a sum of the betas times the infections, okay? And now we have some code where I won't go into this, right? So, but here, this beta, right, that we're talking about is a matrix that we call the contact matrix, okay? And we have some estimates of this, right? I'm going to talk about this a bit later, okay? And then if you look at this, right, so there's out here to solve this model. This is essentially an SIR model, right? You see it's minus beta times the sigma here is actually the beta, right? Yeah, this is susceptibility, right? We didn't need this, right? So I can just erase this. I don't need this at all, right? So this is, you see the lambda here that shows up here is the matrix product of beta times I, right? And then when you solve this equation, you have, I included 4 age classes here at 20 years, intervals from 0 to 20 years, 20 to 40, 40 to 60, and 60 plus, right, of age. I think these are values for the city of São Paulo. And then when you look at this, right, you see that you have now 12 curves, right? So this is a mess, right? So this is 4 classes of susceptibles, 4 classes of infectious, 4 classes of overt, right? I can plot this in a much better way. If instead of plotting all of this separately, all of this together, right, I separate this, dividing each population of susceptibles by the total number of individuals of that age class, right? And then I plot each class separately, right? So here I have only susceptibles, only infectious, and only overt, and each of these lines are already divided by the number of individuals in that age class, right? So this is, they all go up to at most 1, right? So you see here, especially in the one in the middle, right, that when you have for this age at least, you have that age 0 here, that is the first age class for younger people. They go up first, followed by younger adults, then older adults, and then 3 really older people, right, more than 6 years, right? So you see that even for if you sum this, it still looks like the last SIR model, right? The different transmissibilities means that people will not get the disease at the same time, right? So, and this happens because the on-touch matrix that we are using looks like this, right? It means that younger people have a much higher transmissibility rate between themselves. Younger adults have higher than others, and so on and so on. You see that older people that are at this last row and column here have the lowest transmission rates, right? So lowest contact rates. Okay, so this is why the model behaves in that way, right? So let me go back to the presentation now. So okay, so with that, right? So we talked about a bit about age structure. So so what next, right? So what next? So we decided to build the model in this way, right? So so this is what the model actually looks like, right? In terms of boxes, you have susceptibles, right? And susceptibles here, you have to take into account that here, all classes here, all these boxes are actually 3 boxes, right? Actually, because you have S1, S2, S3 for the 3 age classes, okay? And now, besides this, you also duplicate this into the original wild variant over here in the top here, right? And a very similar structure down here for the variant, right? What is the difference between the two? Now they recovered from the original variant, the wild variant. It can also be infected by the new variant. Okay, so you have this arrow over here, you see, right? So this is the main difference between the two, right? Question, right? Could we also include the arrow in the other sense as well, right? From R2 to U1, we could, right? Is it really relevant here? No, because we have a lot of people in this class in the beginning and no one here, right? So this arrow here will be much more relevant than the corresponding arrow here. So we can neglect this other one, right? And the goal here is we have a few parameters that we don't know, and we would like to be able to estimate them, right? What are those, right? So the transmission rate of the new variant, right? That is the beta 2 over here, and the probability of reinfection, right? How strong is or how large is the chance of reinfection by this new variant? Okay, so we have then. Well, this is a large model, right? So you see, our not really large, but like already a lot of parameters, right? So you have incubation period here. You have incubation period here, and then you have the rates, the probabilities of hospitalization, mild disease and asymptomatic disease, and then also the chance of death here of the hospitalized cases. You have the rate of recovery and so on, right? For each age, for each class and so on. And we had already had to estimate a lot of these parameters we got from literature. Okay, we need the population structure, we need the on-touch matrices that were measured in a previous paper. Okay, and we also need an initial condition, right? So when I show you the simulations before, right, I had to start somewhere. What is the initial number of infectious individuals, susceptible individuals, and so on? And usually when in an SAIR model, for a new disease, you just say, oh, I start with a very little number of infectious and let it run, okay? But for this thing here, it is very important to know how many of the individuals from the initial epidemic are still susceptible and how many of them are already recovered from the wild type, okay? So this is also very important, okay? And then we are going to fit what data, okay? So I want you to look at the plots here, but then here, please ignore the lines and look only at the points, okay? The points in this plot here, let me take this. The points in this plot here are the data that we have, okay? So these are the number of new hospitalizations here. So from November until end of January. And these 2 plots down here are the frequency estimated the new variant relative to the total number of cases, right? So we had genomic analysis of this, right? So we had samples of individuals with COVID that were analyzed genomically to determine which variant they had, right? This is Fiocruz data that was released per month. So we have November, December, and January, right? And it went from pretty much 0 to pretty much like something close to 100%, right? 95% here. And for this other data from, this is Nuno and Star Sabino's group, that was almost weekly, right? So almost every week we had data, but with a lot less number. So we have really huge error bars here in this frequency because the number of samples was small in some weeks, right? And without the errors here, this is the data that we have to fit, okay? New cases per week and frequency of the variant, okay? And then the main parameters that we want to estimate are those: transmissibility and reinfection. But there are other stuff that we don't know for sure, right? So the first one is the total prevalence in Manaus. So how many people, what I told you before, how many people are already here instead of here, right? So we had this paper that estimated about 3/4, but also we don't really know for sure, right? So we have this kind of free parameter that is not really what I'm interested in, but I have to take this into account because it's not really a parameter that I know for sure, right? The other parameter that we need to take into account is that when we look at this, right? Okay, in November, we know that very few cases were from the new variant, okay? But when exactly did it start? Okay, the new variant started to grow in the beginning of November or middle of November or end of November. It's really hard to know for sure, okay? And it's really important to fit the data, okay? It's really important because what you see here, these dots here, they are the sum of the new variant with the original variant, okay? And we cannot really separate them, okay? So what do? We started at the beginning of November, but we let free the number of cases from the P1, okay, from the variant, because then if it started only at the end of November, right, it means that this frequency will be fitted to something that is smaller than 1 case, okay, and then it grows very, very slowly, right? So we can estimate more or less the time of emergency of P1 as the time when you had a few individuals already with this variant, okay? This is not really a good way to do this estimate, but it's one way, okay? And finally, we also have to have an idea of the transmission rate of the original variants as well, right? Because if we look back at the data, okay, it's not as if the original variant there wasn't infection going on, okay? So there was infection and the transmission rate is changing over time. And why is that? Oh, because we had, I don't know, you had elections, and then you had the end of the year, the holidays, and so on, right? So the beta here, it also changes over time. And what we're going to actually fit is how much more the new variant can infect relative to the original one, right? And so we need also to estimate the original transmission rate, okay? This is not our focus, but then again, we need this value as well, okay? Well, what does the model return to us, right? So returns errors like this, okay? So given this set of parameters here, it will give us a curve of, here in red, a curve of the number of hospitalized cases of P1 and the number of hospitalized cases of the original variant. And if we sum the two of them, we can compare the sum, that is the black line here, with the total number of hospitalizations observed. And if we compare the ratio of them, right? So the red line divided by the black line, okay, the frequency of the P1, we have these lines down here, okay? So here we take the average over the whole of November, the whole of December, and the whole of January. Here we take the average over each week, right? Each time period that we're looking at the data, okay? And then we have to compare this, right? So this is a fitting. We didn't do this in the most fashionable way, in the most, we did this with a very simple method that is maximum likelihood, okay? This is not great, but not bad, okay? Depends a bit on if you have a long time series, this doesn't work so well, but for short time series, as we have here, it usually works reasonably well, right? And what do you do, right? So you essentially compare you look for different parameters and you compare the curves with the data, and you have this likelihood that you get from this comparison, and the most likely parameters are the ones with these are negative likelihoods, right? So this yellow here are more probable parameters, and then we go over all possible values, or not all, but we look for a large range of values of these 5 parameters here to get what is the best fit, right? With the best fit, and the best fit, you use this curve that is more or less pretty good, right? And this best fit happens for this set of parameters, okay? So we have that the new variant is about 2.6 times more transmissible. Reinfection force was about 3.2%. So if you had COVID before, you are about 30 times less likely to have it again than someone that didn't have it before. But so this would be a relatively weak force of reinfection, okay? So gamma is not very good at reinfecting people, but even with this time possibility of reinfection, okay, only 3%, we estimated that 28% of new infections that happened here were due to reinfections, okay? And this is something that is nice that this group by Star Sabino and her group later did some analysis that got pretty close to this value later, right? So we actually confirmed this was a pretty good estimate. And then we also have estimates of the other parameters that we are not so interested in, right? So, and one that really is really interesting is that the initial prevalence, right? The initial number of people that already had COVID before was estimated as 78%. That is in pretty close agreement with the previous work, right? So this is pretty interesting. This is not something that we forced on the model, right? So we were looking for stuff beginning at 30%, okay? So so this is really nice, right? So and something else that we did that I don't want to go into a lot of detail here is that some stuff is really hard to do, right? So I thought about this one here in the right first is that we had in January in Manaus, right? We had in this region here, we had hospital collapse, okay? We had hospitals that couldn't admit any more people, so people were, it was a really sad period, right? So when some people died at home without hospitals because hospitals were completely full. There was no capacity anymore. People were being transferred all over the country to be hospitalized and so on. But this does reflect in the data that we have. So perhaps the data that we have after this collapse, this was about 10 January, mid-January, maybe this data at the end of January is no longer representative of the reality, right? So we try to census the data. So we do the same thing, but without looking at the last 3 points over here, right? Without taking this decay here into account, okay? And this gives us even more dramatic transmissibility increase, lower infection, but higher transmissibility, right? And something else that we wouldn't do, but this is really hard to, because more data is usually better, right? So we trust more estimates with more data, but it's a really hard situation when you don't trust as much the data that you have, right? So that's why we did this reanalysis, okay? And the other analysis that is important is, well, this assumes that severity, the number of hospitalized cases per infected person, is the same as the original one, right? And this could not be the case. Maybe there were so many hospitalized cases, not because there are so many infections, but because the new variant is just more prone to, it leads to more hospitalizations, okay, than before. But then now there's an issue that with the data that we have in hand, we cannot really estimate independently both the transmission rate and the severity, okay? Because we are only looking at hospitalization data, so we cannot really fit both at the same time, okay? This is a very hard issue, right? So the best we can do in this scenario, right, is to try to use different severities and see how much it affects the other parameters, okay? So we did this with greater hospitalization rates, right? And got pretty much, I think we increased this by 50%. And it still got pretty much the same results, right? So, but this is something that we couldn't really estimate only from hospitalization data, okay? So some of the limitations are this, right? So I already thought about this. We have a large error bar for some of the data from frequency of P1, that is this large error bars over here, right? So this makes life a little bit harder, okay? Because you see that the size of this error bar is from 0 to 50%, right? So this is really, really tough, right? So, and finally, we didn't consider waning immunity, right? So the only immunity that we consider here is original variant. People recovered from original variant were susceptible to reinfection by the new variant. But it could be that there was something else, okay? It could also be that, well, perhaps people that had COVID, the original variant in October, were pretty much well protected, but people that had COVID in April, after 6 months, after 8 months, were no longer protected. You see, so it means that, like, if you look at this plot here, right? So let me begin. Maybe people that were getting COVID here were still immune even to the new variant, but people that got COVID here after 6 to 8 months were no longer immune, right? But then you have to do a much more complicated model in terms of taking into account the timing, right? So your recovered class will now be a much more complicated stuff, because you have to take into account also how long the person has stayed in this class, right? So this leads to much more complicated models, okay? Well, we went for very fast solutions and very fast estimates, right? So we didn't include this, but we were already able to, like in only a couple of weeks, right, to estimate this and to be able to estimate the impact of this variant in other scenarios, right? We didn't publish this, but we showed it to a lot of people, right? So this is the main goal after beforehand, right? So to estimate the impact of this new variant in other regions of Brazil, in other places, right? This didn't lead to a new paper, but it was helpful, okay, very helpful at the time. And this pointed to the need for new measures for mitigation and control of the spreading, okay? Okay, so this is what I wanted to talk about this work in particular. I want to say, I don't have much time, right? So I won't go into a lot of detail. I wanted to talk more about this, right? But this is in the onset side, I hope someone, maybe Roberto has time to
Renato, we had one
talk a
question. Can we go backwards a little bit? I don't know if I missed it. We had one question about confidence intervals of the transmissibility rate.
Maybe I think I'm close to the ending, right? So maybe now it's better to just wait to the end.
Okay, we can circle back. Is that okay? It looks like
Yeah.
it's Flavio.
I see we're very close to finishing, right? So
Okay, we can include it in the Q&A. Go ahead.
okay, so this was in the context of the observatory COVID-19 year, right? That is a large group. The list of names here is of the people involved in this particular work, right? So there's a lot of people, but then this is stuff that the main part of this work we managed to do in like 2 weeks, right? So it was a crazy race, right? It's something that it's really hard to do. Like usual research projects take much longer, but this was done at a breakneck speed, right? So, but this was in the context of this really nice project that we started at the very beginning of the pandemic, and then it grew a lot, right? So a lot of different fronts, from research projects to communication projects, with engagements with the public, producing uh, summaries and statistics for the lay public, and we were involved in a lot of different aspects of COVID throughout the years, right? So I won't have to talk much about this, but this project was born inside this group, okay? And what can we tell from this about what we can do for new variants now, right? So of course, if we want to estimate impact of new variants, the two main parameters, or maybe three main parameters, that it will always be needed, is always the same, right? So we need to know how transmissible the new variant is. We need to know if it is able to evade immunity, right? So it's able to reinfect people that had already had the disease, and we also need to be able to assess the potential for hospitalizations as well, right? How severe the disease is going to be, okay? Of course, now we know a lot more about COVID-19, okay? But immunity is also a much more complicated thing now, right? Because now we have vaccines, and we have vaccination that is very heterogeneous. We have many different types of vaccines. We have different places with different coverage of vaccination, different coverage for 2 doses, 3 doses, second booster, and so on and so forth. The timing of the last dose may be of relevance as well, because after some time, there is some waning. This is pretty much established by now. And also, when it comes to previous infections, we also have a very mixed scenario, right? So different places have had different variants, different proportions of the population were infected by different variants. So the population immunity at this population level is much more complicated than it was at the beginning, right? So at the time of this work, there was only the original type, no vaccines at all. So it's pretty simple to divide the population into never infected and infected by only the original variant. But now we have a much more diverse scenario where it's really much harder to take everything into account, right? So you really have to make a lot more assumptions and approximations in order to look at this, right? And finally, in order to do this, it was essential that we had some data on the frequency of the new variant, right? So we had genomic surveillance, and we would think that by now we would have genomic surveillance well worked out, but this is really not the case, right? Really not the case. So we still don't have genomic surveillance working very well, right? So this is another challenge to deal with in the future, right? So Okay, so thank you. Let me stop here. Okay, so we have time for questions. Yes, thank you. Maybe should I stop sharing or?
Yeah, maybe you should stop sharing. There's a mic on that side, and there was a question about how to estimate confidence intervals for transmissibility. Flavio has a couple questions, so why don't we start with just one, and then we'll turn it to someone in the room, and then we go back to Flavio's second question. Okay, so maybe you can just chat a little bit more about how do you estimate confidence intervals for transmissibility.
Okay, so this is a more technical question, right? So essentially, I wouldn't say this is the, as I told you, I use a maximum likelihood estimation, right? And when you do this, what is this? Essentially, you go over this space with 5 parameters and so on, and you find the parameter combination that is the combination with the maximum likelihood, right? But then, if you look at the neighborhood of this, right? So you can build around this a likelihood, right? And then you have the follow. So you can approximate around this point. You can approximate this likelihood curve by a Gaussian, okay, or by a essentially you use log likelihood, and then you do a quadratic. I'm not sure if I should use this jargon.
I think we're getting, you can, and I think we're following, so you can keep going. We're all imagining your Gaussian near your maximum likelihood. You don't have to draw it.
And then, okay, so then you have a surface. This is a log likelihood, so it's in a log scale, and then you have a quadratic approximation around this peak, okay? This is the top of the Gaussian, right? So because this is log scale, right? And then you just say, well, in this log scale, if I have a difference of where should I draw the line of the 95%? So this is about 2, a difference of 2 in the log scale, right? So this because of how a Gaussian works, okay? So you just look at this and you have a cutoff here, and this determines a region in the parameter space. If you have, for instance, a single parameter, this is a Gaussian, you cut this and you have a value here. It determines a region in the parameter space.
I think, I think we get it.
5%.
Yep, I think we get it. I think probably the question had to do, sometimes there's can be asymmetric confidence intervals or Bayesian confidence intervals, but I think probably Flavio got the idea, and folks here get the idea of how you're going to do it as well. Okay, are there other questions in the room? There's one mic over there. Otherwise, Flavio's going to ask all the questions. You have the mic, so you can ask the question, and behind you as well. And just, you press the button, you just can't tap it. It has to turn green. Yeah, now it's green.
Hey there. Thank you for the lecture. I don't know if you sir are aware, but there is this institute, the German institute named GIS-AID, which they collect data for PCR positive reported worldwide. And there are many institutes in Brazil that they also report to this institute. So they have a collection of PCR positive, and they have the counts. We can calculate the frequencies, and it's released weekly basis. So I wondered if it would be too much to make some sort of multinomial probit model to compare or to try to, I don't know, guess the distribution of these strains of variants among the cases in Brazil. Do you think this will be viable?
So the last part is okay. The error bars that I showed in the plot were essentially a binomial distribution with 2 variants, but if you have more variants and use a multinomial, okay, this is feasible. But then the first part that she says, right? So this is essentially a database of genomic data, okay? But the issue here, and this is a very complicated issue in practice, is that genomic data by itself is not synonymous, is really very far from genomic surveillance, okay? Because what is the issue, right? If you want to estimate the variance in Brazil or in a certain place at a certain moment, okay? You have to do sampling, right? You have to do sampling. Sampling has to be balanced, okay? You have to have some kind of random sampling. So so something that happens a lot in these published databases of genomic data is that they have a strong bias towards new variants, right? Because people that do sequencing of viruses are much more often interested not in population data, in looking at frequencies in the population. They are interested in studying the characteristics of some new variants or something that they detected. Okay, so they are not sampling looking for a balanced sample or looking for the whole population. They are looking for the new case, the new variant. So they are focusing on imported cases. They are focusing on people that present the cases in a clinically peculiar way. They are using on stuff that is different, right? So this is as far as possible from unbiased sample, right? So genomic data is not genomic surveillance. Okay, so we need more genomic surveillance. We need more unbiased samples. Okay, in order to do this kind of analysis of frequencies. I think this is clear. Okay.
Yeah.
Yeah.
It's good, and I think there was a question right behind you. If you could pass the mic one step behind you.
Can you hear me? Okay. Thank you for the lecture. I was wondering how the numbers, the values of the beta matrix about the transmissibility between the ages were determined. I mean, when you showed the code, I saw it was very much precise, the numbers, right? So I'd like to know about this process. How was it? How can you determine these numbers with so much precision?
Well, let me tell you that they're not that precise at all, right? But they're just the result of calculations, and then when they do calculations in the computer, they come out with a lot of with all the digits, okay, if you don't do anything. So, but they're not really that precise, okay? But this data comes from a work by Pren and a large group that essentially this is actually a quantitative social. You have to, in order to get this data, usually what they do is it's not really based on epidemiological data. They go to places and they do interviews with people, and they estimate how long people spend with other people in contexts that could lead to transmission, right? So they interview children, estimate how long children spend with each other, how long they spend with adults, with people from each age, right? And then they try to calibrate this, take into account the different age structures of different populations, okay, and they project it for different countries, right, depending on, for instance, urban populations versus rural populations. So I can't really go over all the details. I think it's really interesting to read the reference, the Spring et al. Paper. It's really nice to learn the methods, but it's really quantitative social sciences, okay? And then we have to rework that. I think the original paper is with age structures of 5 by 5 years. Then we have to aggregate this into the age classes that we had in, and then this is when you have very precise numbers, but you cannot really believe that they're all that precise. Okay? This is just the computer spitting those numbers. Okay.
Yeah, I think we have another. Did you have a follow-up?
No, it's
Okay. Yeah, and just to reiterate, it's true that there are like 4 or 5 significant digits, but they're not significant digits. And it may be worthwhile, Renato, also, we should share maybe that Prem paper. I will also reference it tomorrow. I will figure out a way to get distribution of some key papers to folks who are in this course that you can use for your studies. So we'll try to follow up afterwards with that. That's a key one. There's another question in the room. Before we go back, I believe there was an online question.
Hi, Renato. I have 2 questions. The first one is, what kind of algorithm did you use to perform the maximum likelihood estimation? Because there are a lot of betas to estimate, and to run all the parameter space, it's so difficult and time costing and computational costing. And the second question is, the quarantine and change in the way that the people were used to aggregate, and people that stopped to see the parents, the grandparents, were considered to obtain the correlation metrics, the contact metrics.
Okay, so the first one is a more technical question. This model, it is actually quite complicated in terms of having many local maxima, okay? Many local maxima. Okay, so this, the usual methods, the simplest methods is, okay, you just use a gradient method that keeps following the gradients and reaches a local maximum, okay? But this doesn't work because I have many local maxima, okay? So what we did is essentially combine methods. So we did a initial brute force thing, right? Where we try to map out all of the local maxima, and then we look at the max. We used simpler algorithms for looking at the local maxima for each of those maxima. You see, so you have a very, think of this, you have a very rugged landscape with many local maxima. We kind of made through brute force a general shape to look at where these maxima are, and then we looked at that. We found the peak of each of those, and then found the global one, okay, the one that is the best in general, right? So this is actually a combination of methods, okay. This was not exactly easy, right? But then, yeah. The other question, I'm not sure. I try to rephrase it, right? Maybe see if I get it right.
Yeah, I think
okay,
the
if I get
second
it
question
right.
was, how do you deal with these social contact matrices when people change their social contacts? So do you use the same matrix, or you have to update it?
Yeah, so there is one change that we did that was essential, is that schools were not open at the time, okay? And something that is nice about the spring paper is that they not only estimate the contact rate, but they also divide it into places, okay? So you have school, work, you had others, and you also had, oh, there were 4, right? So school, work.
Probably home was one.
A home, of course, yeah, home, yeah. Home is separated from and others is like entertainment, commerce, and so on, right? So they divided into these 4 classes, okay? And then we essentially took the school part of the matrix, and since there were no schools open at the time, we just set it to 0, right? So we had to adapt to the matrix because schools are a really important part of this matrix, and it wasn't open at the time, right? So we just set it to 0, right? And this is more in terms of, so that the shape of the matrix is not so different from what it should be, right? Of course, in front of the matrix. So the contact matrix will be the matrix itself times this transmissibility, or this beta, right? So we are essentially saying, okay, without spools, we expect that the contact rates between ages will have more or less this pattern, but of course, everything else can change multiplied by the same constant, you see? So, so this is what takes care of the difference through age, okay? But you also could have that isolation, right? So I think it's only called quarantine if you are isolating, if you had contact. I think if you are tested positive, then you are isolated. It's not quarantine, it's only isolation, right? But then we are essentially assuming that since this is a very short time interval, okay, we are assuming that people during this period, they do not change too much their behavior, okay? When we are working with longer time scale, right, when we are trying to fit models throughout the whole of 2020, we had that this beta would vary in time because, well, now there was a lockdown, now we have more use of masks, now we have reopening, and then beta changes over time because people are changing behavior, right? Which we fit only a very short time scale, so that we would assume that, or at least we hope that in this very short time scale, behavior won't change too much, okay? So we essentially neglected this, okay?
Let's probably have to hold there, and I think these questions have raised really open challenges in the field of how does one robustly estimate or even anticipate behavior change, and it's not so easy, and you're right to point out the fact that using these priors amidst this change is going to be at least somewhat problematic or lead to some identifiability issues. Let's thank Renato again for his lecture and for continuing on to lecture despite the fact he isn't really able to travel right now. Thank you, Renato.
Thank you.
And we'll communicate later. I think right now, Renato and I had a little bit of back and forth. We're inclined just to kind of not overwhelm folks. You're here in person, that I will probably take over tomorrow morning's lecture just to give Renato a break so he can keep hydrating and focus on getting better. And I really appreciate the fact that you were able to give this lecture today. We now have a lunch break. We'll come back in the afternoon with Ano Bento's talk and then a hands-on session. Keep in mind for all of you here, everyone is invited. The faculty members, obviously, Renato will not be joining us at the evening dinner, but all of you are invited as hosted by ICTP to a dinner tonight, and you should have gotten an email about that. So that is, whenever that is, this evening, I think 7:30 or something like that. So that's a mini course dinner. Everyone's invited. See you back. I think we're starting at 2 o'clock this afternoon. So be back at a few minutes before 2. That's the right time, right? I think. 2 o'clock, whatever the schedule says for the afternoon session. Thank you again, Renato.
Thank you.